concepts that we've discussed so far. So we know what a connection is. And we know what a metric is. And we know what a metric connection is. In general. And we know what the what a Levi-Cheese connection is on the tangent bundle, which satisfies another condition. And we have various vector bundles. That we have to deal with. We usually call them E. For example, tangent bundle is of fundamental importance, and when its rule is of importance. Then we have, if we have two vector bundles, say E1 and E2, whatever they are, then we can consider the tensor product. This is, yes?
Do you take the tensor product of the bundles or the tensor product of the vector spaces at each one of the bundles?
You take the tensor product, this is a notation which means the fiber product, so it means it's a tensor product fiber-wise.
Okay.
So maybe I should write, this is fiber-wise tensor product. To answer your question, right? That was your question.
Yes.
And I like to remind you of the definition of tensor of two vector spaces. So, so if somebody asks a question, what is the tensor product of two vector spaces? In fact, you ask the question, what is the tensor product of two anythings? Yes, but here it's just vector spaces. The tensor product of two vector spaces. And the usual way of doing this nowadays is to do something very terrible. Namely, you look at this thing, I don't know what the notation is, but let's, I don't know. And I don't know. I really don't know the notation. Anytime something is really big, I write it like this. A script letter for me means it's big. So maybe V12, oh, I know, I will write it like this. Ah, very good. I invented a good notion. For me, that's the formal vector space on the product V1, V2. You understand what I mean? The formal vector space on, there are no relations. So this is the formal vector space on the product V1 cross V2. That means finite linear combinations with coefficients in whatever other field we have here. So the elements of this thing are finite combinations, A1, V1, AI, V1I, V2I, something like that. So it's a free product, there are no relations here. And this is obviously horribly infinite dimensional and something that we don't want to discuss here, right? So we go to this formal vector space, and then the tensor product is just this formal vector space modulo modulo equivalence, where equivalence is bilinear relation. So that means that, let me just write it A1 B1 plus A2 B W1, A1 B1 B1 W1, the equivalence class in this horrible equivalence relation A2 V2 V2 W2 is the same thing as now I have to do this whole thing out. Well, it's the same thing as the equivalence class. You can trust me to do it out. A1, A2, V1, V2, and so on. Yeah, just the bilinear relations in there. Okay, so the usual way to understand these things, I think the physics people here would say, for example, you take a basis E1 En of B1, and maybe the physics people won't like me, I put I here, and F1, no, this is very bad. No, what do you want? Do you want them down or up? Tell me.
Down. Down would be.
Down, okay. So let's not make any index stuff here, otherwise I'll get mixed up. V2, and then the basis of the tensor product is I tensor Ej, Fj, and what that means is this is the equivalence class of Ei Fj. I mean, that's what you do, right? So everybody knows about this, but just to make sure, okay? So it's a fundamental thing to take tensor products, bundles, and we know, for example, if E star tensor E star, the dual, that is what I'm calling the bilinear forms on E, right? And then the basis of the basis here would be forms of the type Fi, Fj, where these are the F1 through Fn is a basis. Well, as a frame of the. Okay. That's E star. E star, for example, I hope you understand what this thing, if you've seen this guy, Hom EF. I'm writing here bundles, but what it means is a fiber-wise tensor product of each thing. If you write Hom, it means fiber-wise homomorphisms of each thing. Everything is trivial over the base. We're just doing this in the fiber, right? So Hom EF is the linear functions from E to F as bundles. And of course, what that is F tensor E dual, right? And why is it F tensor E dual? Because you take something here, let's say W tensor a function F, and apply it to a vector E, V. This is equal to, by definition, F of V W. So that's the way, that establishes an isomorphism of this Hom stuff.
Question.
Yeah.
So a frame is a function on the canonical basis?
What did you just say? No, any frame.
What is a frame? What do you mean by frame?
A frame, we've talked about this many times, but I'm happy to repeat it.
Mm-hmm.
Yes, it is, you take it is a local frame, so it's over an open set, that's the first thing. And if the rank of the bundle is n, it means the fiber dimension is n. This is an ordered basis, E1 through En, of sections. This is the key, of sections. So at each point, this is the basis of the vector space at that point. And so you might call it a moving frame, because if you think of it as this base is moving, it's okay to call it a moving frame. I think that's what some people call it, right? Okay. So these are some of the bundles, and the standard big bundle that is considered in differential geometry is this bundle, namely, and I may put, I don't know what your order is. You physics people have to tell me what your order is. I get mixed up. So first of all, what do I mean by this? I mean the k-fold tensor product of the cotangent bundle with itself, tensor the L-fold tensor product of the tangent bundle with itself. Yeah? And so a section here, or a vector here, is called a KL tensor. And that's where I'm afraid I will always make a mistake whether it's an LK tensor or it's KL tensor, but I think it should be called so let's just test that. So typically a frame here would be dx I1 tensor dx ik tensor in this basis of the coordinates tensor. Okay, I'll write it out long. dx. What did I write here? This is terrible. Ik j l, no, not l, j1 tensor. Okay, you tell me if I've gotten the numbers right. j l. Do I have the numbers right? Is it a KL tensor or an LK tensor? I think I got it right, yeah?
Yeah.
You understand? We take a basis, we take coordinates. And then we have the associated frames to these coordinates of the tangent bundle and cotangent bundle, and then we take these associated frames. That's huge in general. Okay? That's called a KL tensor. Okay. And those are the fundamental associated bundles that arise quite often in our case. Okay? It's a little bit formal, but at least you know the notation. Okay? And people in physics deal with these things all the time. Okay? I will talk later today about something called curvature, the first Riemannian curvature. So curvature, now to get it right, I got it right, I think, is a 1-3. Okay, it will be a 1-3 tensor, Riemannian curvature, whatever it is. So that's a little bit about what we know so far, with a small diversion into the formalism of tensor products, which you need to know. Mathematicians, if you talk to any physicist, you need to know this. Yes?
So we know what the tangent product of two vector spaces is, right? But then when you write Fi plus Fj, that's two elements in the vector space, right? So how do you define the tangent product of two elements in the vector space?
I'm not sure I understand it. So we have, let me start again and tell me to stop when you don't understand. you're talking only at the vector space level, you accept that the bundle level, you just tensor the fibers and everything goes through. And the tensor product is just the formal formal product. What do you want to call a vector? V tensor, V comma W. And that spans, all those things span a huge vector space. And now we take the equivalence relation by linear things. And we get a finite dimensional space. And the equivalence class of two vectors is called V tensor W. That was your question. The equivalence class of two vectors, this huge infinite dimensional vector space modulo by linearity is, okay? And you will see that when you talk to your physics friends, that they will tell, I'll get you right before, that they will, you and I will say this is an operator, or we take a basis and say that this is a matrix. But quite often you will see your physics friends call that a tensor. Yeah, you see, of course it's a tensor. It's in Hom. No, it really is. That's the way, it's a good way to think also. Okay, I just, yes, your question.
So when you take the formal linear combinations to get the curly field, right?
You're talking about this form,
Formal linear combinations. Go up.
yes, just any here.
So both of the vector spaces have to share the same field?
Oh, sure.
Yeah.
At least for me, I don't know any tricky way to avoid that. But that's a good question, of course. Of course, if you have one thing's the real numbers, the other thing's the complex numbers, then you can do some. You can regard the real numbers as
Yeah, but it only no.
yeah. You can regard everything as complex and then do it.
Yeah.
And it is quite often the case that we want to think simultaneously over the reals and complex. So, but
They have to share the same.
yeah, I think I would. So, by the way, what Abig's talking about, quite often, you will see this notation. That's what he's talking about, exactly, right? That we're tensoring over the field R, that means the bilinear relations are the real. Implicitly here in our lecture so far, everything is over the real, so I didn't say that. But that answers your question completely. Okay? Thank you. It's good to do these things, otherwise there's some confusing, particularly when you're talking between subjects, physics and mathematics. Okay, so we have these huge bundles and lying around, and we have to deal with that. Now, we saw that there was we had a Legendre transformation. Transform, going from, for example, if we're talking about geodesics here, going from the tangent bundle to the cotangent bundle, and using the Lagrangian for geodesics. Yeah. And that simplifies matters immensely to the cotangent bundle, where we have a standard structure, a symplectic structure. So this is a standard symplectic structure. Which we talked about quite a bit in depth. And the key is here for us in this case, and in many cases, the geodesic equation becomes a Hamiltonian equation. So the geodesic equation is Hamiltonian. Which is called, as you know, the Lagrange, or the Lagrange equation. This equation becomes Hamiltonian. It's Hamiltonian. And the Hamiltonian is just the duometric, so, and the key thing is we already immediately have some invariant. Have a certain invariant, at least two invariants. standard, in this case, standard structure as invariance. And these are invariants of what I call geodesic flow, which means the flow of the local system. Geodesic flow. Okay. Now, recently, I'm making a huge jump in history. This is the Euler-Lagrange equation. Euler gave a famous lecture on this subject in 1756. And not much serious happened until modern times. And in the very modern times, Gromov told us and I thought you might be interested in this paper, so of course I read a paper. I never read a paper carefully. I just go through it and try to understand what he's saying and then think about it. And so I checked it out again for you. This is a beautiful paper. A 1985 Inventio. I think it's a unique Inventio in this paper. He showed us, he really showed us how to use symplectic structure in combination with complex structures. So it showed us how to think about a combination of symplectic and complex structure. And I feel you should keep in mind that Gromov is a differential geometer, or just simply a geometer, but really also a differential geometer. So he works in the area of this class. But he uses all technology he can get his hands on and invent. Very unbelievably creative mathematician. And so he discusses what we call J. Everybody in this class has seen a J. So we have a J which, I'm formalizing this now, that's a bundle endomorphism. Okay? That's a bundle as an endomorphism, and you should think of that as a multiplication by I. Yeah? That's what it always is. And that's that. But to re-emphasize this in a very strong way, this is a fiber-wise defined, varying smoothly, of course, bundle at endomorphism. It's an infinitesimal complex structure, is what I like to call it, at infinitesimal level. Okay? So let's just call this a complex structure. In the literature, the original literature several decades ago, this was called an almost complex structure. Okay. And this does not necessarily come from coordinates. So if you have coordinates, holomorphic coordinates, Z1 through Zn, then with, say, Z I equals, Z alpha equals X alpha plus I times Y alpha. Right? Yeah. What's wrong out? Everything? Okay. If you have such coordinates, then you can define J as well defined because the coordinate change of variables is holomorphic. J is well defined by J of ddx alpha equals ddy alpha. It's what you think it should be. J of ddy alpha is minus ddx alpha. So if you have such coordinates, then this defines a complex structure. Let's call this thing up here infinitesimal. So at the infinitesimal level, and really at the tangent space level, decimal level, and this thing, a complex manifold. So the space, so here, okay, good. So many infinitesimal j's are not given by coordinates. So the way you should think about this, Gromov defined a very big class of j's that was very good. So Gromov calls these things omega. Omega is a symplectic structure. So omega attained structures. And I'll emphasize infinitesimal. So at the tangent bundle level only. And the space of structures which are coming from coordinates, so let's call these complex manifold structures. This space of complex manifold structures is very, 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 very small in comparison to the space of infinitesimal structures. You look mystified now. No? Where are you? Am I losing you?
Okay, so there are many j's that are not given by coordinates.
That's right. That's all I'm saying here. Okay? And what I said is, you don't need this condition omega attained, but let's recall what that is, just for fun. Omega JV JW. So J is an isometry in the sense, and GVW, which is defined to be omega J. VW is a Riemannian metric.
The moment you get these holomorphic coordinates, you automatically get a complex structure.
Yeah, I just told you how to do it.
Exactly. But you can also have a complex structure without having these holomorphic coordinates.
That's what I'm saying, and I'm saying this is, the comparison of the two looks like this. Even if you impose the omega attained condition, which we talked about last time, which cuts it way down and makes it compatible, tame is really the good word, makes it really good, behave well with respect to the symplectic structure, this space is still very big infinite dimensional. I mentioned this last time. It's an infinite dimensional contractible space, and in this thing you have these structures which are really complex manifold structures, and that's what I mean by here. Okay? Okay? And let me call this thing star. The equation for star, there's an equation, is the vanishing of what is called the nine-house tensor. I told you about this last time. So it's really very, usually you can think of this thing as finite dimensional and this other thing is just hugely infinite dimensional. And that's a tremendous advantage in terms of flexibility. You can move things around, you can consider curves of these things. You don't see it yet because we haven't worked with it yet, but this is Gromov's point. Okay? One of his points. Are you okay with that? I've avoided the notation. Maria, you're almost asking a question. Not quite. I've avoided the notation almost complex structure. I think the people in the business now just don't, they get tired of saying that. And they just say complex structure, but then they'll say in this case, one thing they will say, by the way, in this case, they will call this an integrable complex structure. And the reason they say integrable is you have to integrate certain differential equations to get the coordinates. You can imagine, right? Okay. Now that was a little bit of a sideline, but maybe future music if you are interested. And I'll tell you people in physics, the physics community has not yet understood the depth of the development in the mathematics community in this subject. I know that for a fact. There are very few physicists who really understand what has happened since Gromov. And if you're interested in this kind of thing, I would really recommend you think about it. Okay, so we are poor mathematicians, so we, let's study only omega tanh structures which come from coordinates. Up to this point, this was somewhat of a review of my last lecture. Okay. Now, the funny thing about this is, so let me just write again what that means. We have a symplectic form, so m omega is symplectic. And it's a complex manifold with structure J defined as above. Right? But it's a complex manifold. You really have coordinates. Okay. And let's just regard this for us as we're looking for a very good class of such manifolds. And in Riemannian geometry, why? Why in Riemannian geometry? Well, this why is easily answered by the following thing. You define H to be G minus I omega. I hope I sent the notes, and I hope I get the sign here right. There are usually very good reasons for a sign, and I think this is the right sign. Yes? This is symplectic. This is Riemannian. And this is a Hermitian form on the tangent line. You all know when you have a complex structure or a complex vector space, the right form on the complex vector space is Hermitian. Right in the sense of correct. Okay. So this is what's going on. You have this nice combination of symplectic Riemannian. So any two of the three gives the other. So we have a very strong connection using this J to Riemannian geometry. It's the same subject in some sense. Okay. So that means, in my opinion, we should look for examples. Of these manifolds, which are called Kähler manifolds. Now, the Kähler is just the name of a mathematician, it doesn't matter. Now, I will tell you how he discovered these manifolds in the 1930s, so before the war. He lived long after the war. He died well after the age of 100. Was a professor here in Hamburg, not very far from here. And he discovered these manifolds in the following way. He didn't know that this was, what I'm going to tell you is his definition, but it is a lemma proved by Kodara. Kodara's lemma. If omega is scalar, this will look almost is scalar. The symplectic form is scalar form. Then omega has a potential. Now, I'll remind you of absolutely everything here, but I'm going to say a word first. These kind of functions are extremely important in all forms of analysis, so where rho is strictly purus over minor. Taylor's definition, by the way. He understood the role of these potentials much better than he understood symplectic geometry, and he defined the form by having a potential. Why not? That's not very good. Let me just repeat this. So let's do an example before. Let's let rho equal norm of z squared. It's a reasonable function. In complex analysis, I hope you've seen this function appear as being very important. Or functions of this type. Now, you've forgotten complex analysis because I was a bad teacher, so I will tell you what complex analysis is. This is probably something like this. Right? We talked about this in great detail in complex analysis. And these are the two operators. Well, once you know one, you know the other. And you recall that f is holomorphic, if and only if d bar f, which is equal by definition, df dz bar equals 0. So already the d bar operator is going to play a role. And now let's see what dd bar. Let's look. I'm going to make this thing real. It's important to make this real. So I over 2 dd bar of norm squared. This is just some fun. Yeah. Let's compute this. This is I over 2 d of d bar of this thing. So I'll write it out. D bar of z bar. I over 2 d. And now, from the point of view d bar is holomorphic, so this is just z bar dz. And what do I do? Yeah, no. I did z bar first, so dz bar. Right. So d bar of this, z bar, z is constant. We have two variables, we think of them. And that's that. And I'll take d of that. This is equal to I over 2 dz, dz bar. This is just some calculation that you can do at nighttime when you're really in bad shape. So, that even I can do. So now let's see what dz is equal to dx plus I dy. And so dz wedge dz bar is dx plus I dy. Wedge dx minus I dy. And dx wedge dx is 0, and dy wedge dy is 0. So we have dx times dy with a minus I, and the same thing here, so it's minus 2I dx wedge dy. And so, as you see, I over 2 times this thing is dx. And now I shouldn't have, for the physics audience, I should not have written that. I remind you, i.e. it is dq dp. So the potential of dq dp is the norm function. Okay, is the norm function. The potential of dq dp is the norm function, norm squared. Norm squared, of course. Yeah, that's fundamental. It's Laplacian, which we just calculated here, up to a constant. This operator here, which we effectively calculated, is effectively the Laplacian. And the statement is that these functions that we get here, you take the Laplacian of these functions, and the Laplacian is positive. Yeah? Okay. Well, let me tell you what that means. But if you have a boundary value problem, value problem, and you write down. Well, I don't want to get into this. There's a good reason for calling these functions subharmonic. They lie under harmonic functions with the same boundary value, and they satisfy the maximum principle. So if you've done any complex analysis at all, you know essentially the only key theorem is the maximum principle, and these things satisfy the maximum principle. Okay? And Taylor knew all of that, so he decided to define special manifolds called Taylor manifolds so that omega has a potential locally, which is strictly subharmonic. Kodaira proved if you have a Taylor manifold, then in fact it does have a potential like what Taylor wanted. That's just an elementary level. But for me, elementary because I know some complex analysis. But it's very interesting. Yes, this circle. Yes.
So what would the definition of Clarice?
You know I have trouble hearing you, so I have to come over.
What would the definition of Clarice harmonic?
Yeah.
Functions?
What's that word?
So, let's look at it here just for fun, okay? Plurisubharmonic, why pluri, first of all? Many variables, okay? So the first discussion of subharmonic was in one complex variable. So it was called subharmonic function, okay? And there were reasons for calling it that, okay? But the good reason from our point of view of this is if you look at this thing having that potential, and you want this thing to be Riemannian with no degeneracy, Riemannian with no degeneracy, yes, that is absolutely equivalent to the function being strictly plurisubharmonic. It's a question of eigenvalues of the Riemannian metric. You're not happy.
So given a function, when is it subharmonic?
I just told you.
Right.
Take dd bar of it. Okay, you can do that. Anybody can do that. Computer can do that. Take dd bar of it. That is a 1-1 form, right? What do you say that a 1-1 form is positive definite or negative definite or blah, 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 blah? If the associated Hermitian form or Riemannian form is positive definite and so on. So I just said something is strictly plurisubharmonic if you take dd bar, as I just did, and the associated thing is a Riemannian metric. So positive definite. Okay? And you should be excited in the course on differential geometry because I'm telling you how to make Riemannian metrics coming from the viewpoint of complex analysis and symplectic geometry. Alright? Am I not telling you that? You start with omega, j, and so on. Yeah? Okay? And I'm telling you, be closely related to this, the Laplacian, and believe me, it is very closely related to Laplacian. Okay? So you know anything in physics, you look at eigenvalues or Laplacian and so on, this is a very central thing that's going on here. Right? Okay. Are we okay with that now, Marie? Thank you. I really appreciate all your questions. Sometimes I get excited. And, okay. So now I will attempt to explain a fundamental construction. So example 1, let's say example 0 I just made, but let me make that a little bit better. Let rho equal norm squared on Cn. And then I over 2, this just makes the thing real. V bar rho equals omega is a Taylor form. When I say that, I mean the manifold is scalar with respect to that form. I just did it. I mean, I did it for one variable. Well, that's not so interesting, but I'll tell you something that's very interesting. This is example 1. And I highly recommend that you spend a lot of time just thinking slowly about this example. Okay, example 1 is the, let's call it, it has a name, the Fubini Studi. I don't know too much about this person, this was German, I think. Fubini Studi Kähler form, Kähler structure on P and C. Projective space. And I will do the calculation. It's even interesting for P1. Okay, so let's do it for P1 and then you can have fun doing it for Pn. The notation, there are enough physicists, they're good at notation, physicists. So just talk to your physicist and they'll get notation right and mathematicians will screw it up. So I think it's enough for doing it for P2. So for n equal 1. That's a compliment, don't be insulted. Yes, I mean it is. Okay, what is this? So, what is the definition? You have C2 minus 0. Fibered over P1C. Okay. Everybody here has seen this vibration, I think, I hope. Feedback, is that okay? This usual vibration. So the equivalence class of a vector is C star times this vector. It's the line, we call this a line determined by the vector. Okay. And so I always write this with the C star here to indicate that that is the fiber. Okay? Now, a little bit of future music. Just so you get used to some of the words. This is C star principal bundle. You've heard the word principal bundle, and this is the first time you will see a good one. Okay? Okay. And now the picture of this guy, a girl, I don't know which it is this. Here's P1C, and here's the origin, and here are all these lines through this thing. And these are the equivalence classes. So for example, if this is V, then this thing here is the equivalence class C star V. Now, this is the only thing, I mean, we have a rather short lecture today. This is the only thing you're going to learn today, at least for me, is if you see something like this, you want to push down the structure. I hope you see some situation like this, you want to push down the structure, right? You have a structure upstairs, you want to push it down downstairs. That's the first thing to try to do, but you know this is a positive dimensional fiber. So it's not so clear you can do it. You just have a few points upstairs in each fiber, you believe you can push something down. Here you can average over those points. But here, what can we do? You might want to integrate over something, maybe that'll work, but I mean, that's a non-compact fiber. Yeah, pushing down is maybe a non-trivial thing. So the idea for Euler is to push down a potential. Yeah. Euler said you should have a potential, and for this, yeah, why not? Let's try to push down a potential. So let's try rho equal to norm. Oh, let's say that's this is P1, so this is C2 minus 0. And so the coordinates here are Z1, Z2. And let's try pushing down the norm squared of Z, which is norm Z1 plus norm Z. Well, what happens if we multiply rho of lambda times Z? What happens to this? Well, that's even good, but it's bad. Because what you get is absolute, you see, what we're doing, here's V, I call it Z, and here's lambda times V. You would like to have the same potential here, so you could get it downstairs, right? So this is terrible though, look, because it's lambda squared times the rho of Z. Right? And that's not going to work. I could take dd bar of this thing, and it's still bad. This will survive, this bad norm. You understand what I'm saying? This lack of periodicity, if you wish, will still survive. Yeah? And it doesn't take very long to realize there's only one thing to do here, and it's this. So let rho be some sort of function of the norm, So that when you take dd bar of that function, that thing, it's periodic.
Okay. So a K form is what we would get if we take dd bar.
We got a two form.
Yeah.
Yeah.
So we get the two form that we want. Why do we suddenly have a requirement on this two form? So besides
Because I want it to be downstairs. If this two form is not in some periodic with invariant with respect to this vibration that we have, it's not going to exist downstairs, right? I want it downstairs. Yes.
I mean, lambda squared is going to be in the same fiber, so why can you just...
That's right. And so that's right. If I use this norm function here, this is going to be the effect of the fibers. You're going to take dd bar of it, and it's still going to be in bad shape. Okay.
Why would you want it to be just lambda times rho z? Why is that a bad thing? I mean, if you just collapse it, then...
I want it to exist downstairs. I want lambda to vanish in this discussion when I take dd bar.
So do you want lambda z to be the same on the part of the fiber?
Yes.
So you can say, well, it's equal in all the fibers, so I can push it to this.
What do you, no, lambda's going to be it's going to be the same action in each of the fibers, but it's not going to be the same number.
Yeah.
It's any element of C star.
Okay. Yeah, I see.
Okay? This is a very important discussion. The general discussion, I have a principal bundle like this, I have a group in a fiber, I have the group acting on the fiber, I have object upstairs, and I want to push these objects downstairs. If the group is finite, you average over the group. That is stupid. If the group is not finite, you don't know what to do. If the group is compact, you integrate over the group. Because you have, right, I mean, you have no fear of compact integrals over compact things. But you cannot integrate over this or something. You have to have some idea. Okay? Yes.
You can't just project it downstairs.
What do you mean projected?
Well, you go from the equivalence class of V to just, V. Or
Okay.
the first ordinate of V.
Okay.
Something like that.
Okay, there are two ideas here. Let's call this idea the Maria idea. It's called the projection idea. Yes? And let's call my idea that I'm going to sell to you in a minute, Allen idea. And I'm just going to sell it. I'm not going to claim it's a good idea. And then I'm going to explain how you're right, and then we're going to quit the lecture, okay? You have time and patience to handle that? Okay, first of all, I think the Maria idea is deeper than the Allen idea, so I'm going to explain it second. Okay? So anyway, I want somehow to kill this problem with multiplying by this lambda, and so the obvious thing to do is to take log. Because why is it, or do you call it ln? I don't care, the log ln. Yeah. Why is that good to do? It changes multiplication into addition, right? And if I take two derivatives, I kill the lambda, right? If I take two derivatives, I kill the lambda. Yeah? So let's take this and let's make sure it's real. And this thing is lambda periodic. Okay? All right. Okay? And now let's just have some fun. Let me compute this in the case of P1, which we all know is the sphere, right? So, so let's compute this. Let's compute omega dd bar I over 2, well, I over 2 dd bar of log z1 squared plus z2 squared. Wait a minute. Wait a minute. That's still upstairs in some sense, right? Right? That's still upstairs, but it does not depend on anything anymore. So, on the chart, z2 not equal to 0, and so that would be I over 2 dd bar log 1 plus z over 2 z squared. No, the other way around, right? I divide by z2, z2 squared, z squared 1. Yeah? You see what I did? No. Okay. Upstairs, we have coordinates z1 and z2. This form doesn't depend on lambda. So it exists downstairs.
Okay.
Okay. So I compute it downstairs in the coordinate z. Z is the coordinate z1 divided by z2. Okay, there it is.
Okay.
Well, this is what this is. I think if you do it out, I hope this is right. I've done this many times in my life, so I am virtually sure I did not make a mistake. Okay? Now, that is the absolute canonical form, or 1-1 form that I can get by this procedure. You try anything else, it doesn't work. If you try any other function of the norm, it will not kill the lambda multiplication. That is the standard metric on the two-sphere. That is the standard metric on the two-sphere. Let me explain to you why it's the standard metric on the two-sphere. Well, in this picture I left something out. Guess what that is? That is a sphere upstairs. That's the sphere in C2. Yeah? Okay. That's the 3-sphere in C2. Okay, this 3-sphere fibers over here is an S1 bundle. That's called a Huff bundle. It's an interesting bundle. The 3-sphere fibers over the 2-sphere in the so-called Huff bundle. Physicists know about this because a state is really an element in projective space. A state is down here. But physicists don't like projective geometry, so they go upstairs in the vector space. However, they are willing, you will tell me this, they are willing to scale the state to have norm 1. So they scale the state to have norm 1, which is good. And then they talk about something called phase. Because this intersection here is not a point, it's a circle, right? It's a circle. So they talk about the phase being parameterized by that. So this is the fundamental first bundle you would ever consider there. Okay? Now, I told you last night, have you eaten already? So I will go a few more minutes to explain Maria's idea. And then, okay? Okay, watch. This is my idea, but now Maria's idea. Maria says, well, what I want to do is just define it here someplace and push it down. Okay? Let me write this as pink because it's a very good idea. She says, let us define it. I want to tell you what I just did. I said, anywhere you define it, it doesn't matter because it's periodic. Right? Lambda is no longer involved in this thing. Anyway, where I divide, so what did I do? I take, say, a vector here, or a pair of vectors here. I lift them anywhere up here. It doesn't matter here, 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 here. Because this is all invariant, I get the same answer. Okay? So my idea is roughly your idea, but I like your idea better. Watch. fact, I love this idea. Watch. It would be well worth your time to think about this example. Here's a really better idea. Okay, what color is the sphere? S3 is orange, right? Okay. Here is C2. Here is the 3 sphere. S3. Okay, that's the 3 sphere. Now I'm going to do something. What's the dimension of the 3 sphere? 3. 3. So I'm going to draw its tangent space any place. Here's its tangent space at any point. That's the 3-dimensional vector space, right? Right? Sorry. If I give you a 3-dimensional vector space in a complex vector space, if you're ever a professor, please remember this lecture. Never do real geometry on its own. Never do complex geometry on its own. Always watch the mix between real and complex geometry. Okay? I give you a 3-dimensional real vector space in a complex vector space. Okay? Okay. What is that dimension, odd or even? Odd. It's not a complex vector space then. Right? If you take that space, which is 3-dimensional, and take I times it, I times a space will be another 3-dimensional space, right? Right? Those are two 3-dimensional spaces in a 4-dimensional space. What do they intersect in? A 2-dimensional space, right? Right? But that 2-dimensional intersection is invariant by multiplication by I. Right? Because I took the 3-dimensional space and multiplied it by I intersected, right? That says in any 3-dimensional space, there is a unique Maria space, which is the unique complex subspace of that thing. Okay? So this says that there is a unique Maria space tangent to the unit sphere. You physicists listen to this because most physicists do not know this, and this is fundamental. This is fundamental because this kills phase. So, what is that? Let me draw the picture up here. There's a unique, at any point here, there is a unique Maria space, which is a complex space tangent to the sphere at that point. Didn't I convince you of that? I mean, 3-dimensional real tangent space, I times it, intersect. That's a complex line, right? Right? Well, Maria said, if I have two vectors down here, I just want to lift them up here and take whatever it is. Right? Okay, do it. That's it. That's exactly the same thing as I did. Okay? You wanted to have a fixed point where you could understand it, and I said I didn't care because it didn't matter, basically. But I like much better what you're doing. You say, I have this canonically defined, like a section, yeah? And you say just lift and take the product. You're right. But the trouble is, what happens is, as you know, this unique space is not unique for all your points. So depending on the point, you have to change the space. But it's okay. That is the first example of a connection on a principal bundle. And this was discovered only recently, maybe only 50 years ago. The fundamental thing, this is a principal bundle, you have a horizontal subspace, what I'm calling Maria space just for fun. But it's very useful, right? Because you can just go up there and take the inner product. Okay? So this is very nice. And this is an example of the Fubini-Studi metric, which is the round metric on the two-sphere. And of course it's the round metric because it's invariant under the full group here, which is the full orthogonal group. It's the unique round metric. Okay? And I dare you to try by hand to compute the geodesics. And after you've failed, go to Khan Academy, as I suggested, and see, I mean, it tells you nothing, but it's sort of fun to see what these people do. Okay? Thank you for coming today.